Here we're going to talk about the human ear. We can see here the electromagnetic spectrum, frequencies shown on the left-hand side here in the vertical axis, and sound frequency on the horizontal axis. All you hear and see is in here, which is not very much. Here we're going to talk about the range of human hearing. So there are a lot of sounds that we cannot hear because they're simply too high frequency or too low a frequency. If we have a look at the outside of the ear, we've got several different components or parts to the outer ear. The pinna, which is sometimes called the ear flap or the auricle, and the ear canal leads to the tympanic membrane or the surface of the eardrum. And this is kind of like, if you look at this shape, it's kind of like a cone shape, or if you like to cook, you might think that looks kind of like a funnel. And it has a job that's very similar. It's there to collect as much sound as possible and channel it down to the eardrum, kind of like using a funnel to pour liquid into a bottle. Now remember that sound is a pressure wave, a longitudinal wave that changes depending on the frequency of the source. So the arrival of those high pressure regions or compressions of the air molecules at a certain frequency will push on the eardrum at that same frequency. The arrival of the low pressure regions will allow that eardrum to relax and it will move outwards again. If the frequency of the arrival of the compressions and the rarefactions is high, then we hear a high pitch sound. If the frequency of the arrival of those high pressure and low pressure regions is low, we hear a low pitch sound. Yeah, I'm not going to quit my day job, don't worry. In the middle ear, we also have several important components or parts. We've got 3 very small bones in the middle ear, commonly known as the hammer, the anvil, and the stirrup. I won't test you on the true biological names, you'll learn about those in biology class. Collectively, these are known as the ossicles. Right in here. They're very good and efficient at transmitting sound because they are solid. Sound will travel faster and more efficiently through solid materials than it does through gases like air. That's why we can hear sound through metals very easily, even if the sound has traveled for miles. Like putting your ear down against the train tracks and you can hear the train coming many miles away. Please don't do that if the train is in sight. Not a good idea. So when that eardrum gets pushed and pulled out by the pressure wave, it causes the bones to vibrate. And these vibrations transmit those sound waves or the sound energy into the fluid of the inner ear. So we've got some fluid in here. We call these the semicircular canals. The semicircular canals help us to maintain balance. So if you go on a spinny ride and you get dizzy and you lose your balance, that's because you've disrupted the fluid somehow in those semicircular canals. If you get an inner ear infection, then that can mess with your balance as well. For the same reason, we rely on those fluids and those semicircular canals for our balance. That can change as you get older, too. I'm not so good with the spinny rides anymore. Now, as that fluid moves around in the inner ear, it'll move in the part of the ear called the cochlea, which you saw in the previous diagram, which looks kind of like a snail's shell wound up into a spiral. But if we could unravel that spiral, we would see a long tapering tube with tiny little fibers or hairs all the way along the tube. And they go from fairly long at one end to really, really short at the other end. And each of those fibers or hairs will vibrate according to a certain frequency. So the longer ones resonate at lower frequencies, and the shorter ones resonate at higher frequencies. Once they resonate, they'll transmit those signals to the brain through the auditory nerve, kind of like the optic nerve does for the eye. And the brain will interpret those sounds. If you're exposed to a certain frequency of sound over and over again and it's quite loud, you can damage some of those hairs and become selectively deaf at those certain frequencies. So of course, as those signals are transmitted to the brain, we're really using the nervous system to help us distinguish between the frequencies that we hear. Intensity of sound means how much energy we're receiving from those sound waves. High intensity sound waves have large amplitudes. Low intensity sounds have very small amplitudes. High intensity sounds can damage the ear, not just the cochlea and the hairs inside, but also the eardrum, depending on how high the intensity of the sound is. Those cochlea hairs are very, very sensitive though, and so if you work in a loud environment, you'll probably be required to have hearing tests done frequently and wear hearing protection to make sure that you're not damaging your ears. So how loud is too loud? Well, if you're exposed to 110 decibel sounds for more than a minute, or 100 decibel sounds for more than 15 minutes, you can get some permanent hearing loss. And we can see here some examples from the decibel scale. 130 decibels is the threshold of pain, so you'll be in physical pain if you're exposed to a sound that loud. Rock bands, 110 decibels, so some rock musicians have hearing loss for that reason. Jackhammers are also very loud. And then regular conversation is about 60 decibels, so those are some good examples. Prolonged exposure to any noise or sound above 85 decibels could cause gradual hearing loss. And over time, most of us get hearing loss just because we're exposed to a variety of sounds. The blue whale can produce sounds up to 188 decibels, which is extremely loud. And they, of course, can communicate over long distances using those sounds.